Now it's fine. Yes. Still, people have to join. Hello. Hello.
Yes, sir.
I was just checking. I don't know why. So Anthony joined. Aditi still didn't join yet. Okay, fine. Let us start. Okay, right. So we have completed equilibrium, ionic equilibrium as well as the normal equilibrium, right? So today we'll be starting with gaseous state, or it's also called as states of matter in some textbooks, because we will be dealing little with liquid state also, but not much. And the JEE point of view, and I have never seen questions coming from liquid state. So we will just try to just touch up whatever we have, but not so much, right? Okay. Fine. So like this chapter you must have already known, because you must be like, we used your ideal gas equation, Boyle's law, Charles law, all these things in different aspects of chemistry, especially in thermodynamics. We used it, right? So fine, we know what is a gas, we know how is it different from all the other states of matter, all these things in terms of kinetic energy, in terms of intermolecular space, the force of attraction and all that, right? So let me give you a quick this thing about the chapter, and we'll straight away go for the problem solving, right? So fine. So first, and like this is not going to be a other like other chapters. I'm gonna not gonna so go in depth and teach you, but wherever required, yes, definitely I'll do it, right? Okay, fine. So starting with the chapter starts with actually what is a gas, how the pressure is developed, and all these things. We know how the pressure is developed, isn't it? So it's because the gaseous molecules are going to be in continuous random motion, right? So they're going to hit the walls of the container, right? So there'll be a force with which they will hit the walls of the container. So that force divided by the area of contact is what is my pressure, right? So anyways, so now a temperature, again we have a physical sense of what is temperature because we completed thermodynamics. Volume is again going to be pretty simple, right? So it's the space occupied by the gaseous particles, or for that any state of matter, right? Fine. So there are going to be laws which is going to connect these three things. I would say four things: pressure, volume, temperature, and number of moles. There are going to be laws connecting this, right? So the first one among this is what is my Boyle's law, right? So at constant temp, we know what it says. At constant temperature, the pressure and volume are inversely related, right? So at constant T, right, the pressure is inversely proportional to volume, right? Or I can say PV is some constant, right? So now or even I can say P1 V1 equal to P2 V2. It is going to be equal to some constant C, right? Okay, so you will be able to apply at two different states, right? We know what is a state. State means the conditions, right? So at initial pressure and final pressure, like if you do something and you change the volume of the gas or you change the pressure of the gas, you'll be able to, and again, given that the temperature is constant, right? So at that time, I'll be able to use Boyle's law. Okay, so if I the like a lot of questions will come from graph from this chapter, right? So if you look at the graph for T versus V, right? So you can see it's inversely related. So I'm going to have a rectangular hyperbola, something like this, right? So as pressure increases, you will see volume is increasing. Okay, now I can make the question a little more interesting if I draw a graph, right? Say this is one graph, right? Say this is another graph, this is another graph, right? Say now I'm going to get three different graphs at three different temperatures. These are what are called as isotherms, right? Isotherms are graphs plotted at constant temperature, right? Say if this is our temperature T1, second is a temperature T2, third one is a temperature T3, and if I ask you to arrange T1, T2, T3 in the ascending order or descending order, can you tell me which is higher, which is lesser?
T3 is higher, T1 is least.
Okay, fine, we'll check. So now whenever these kind of problems are going to be given to you, you take one volume or one pressure, right? And you see how the temperature is varying along with, say, the pressure or the volume. Say I, for example, say I make volume constant or say pressure constant. Let me take pressure constant. I will take one particular pressure, right, for all these three isotherms, right? So now I'll check what is the volume in each of these cases. Okay, so this is corresponding to T1 graph. So this is V1, V2, and V3, right? So now I see from the graph, obviously this side the volume is increasing, isn't it? That is the volume coordinate, right? So this side the volume is increasing, so obviously V3 is greater than V2, greater than V1, and obviously that will happen. Now we know temperature, when I heat something, obviously the volume is going to increase. If I supply more and more heat energy, or if I increase the temperature, the volume of the gas molecules will keep on increasing. Again, given that it is going to happen on constant pressure. Now that's actually your Charles law, correct? Yes, right. So fine. So you can see volume is like this. So since my temperature and volume are directly related, right, I can also say that T3 is going to be the greatest than T2 than T. Okay, now if you're going to do the wall, if you're going to make volume constant, do the same thing, right? If you just they make a volume, some random volume you take, and you take the pressures of all these three, again you will see that P3 will be greater than P2, greater than P3. So again, temperature and pressure are directly related. Given that the volume is constant, you will be getting the same value, same order for temperatures. Okay, right. Now if I give you a graph for uh, PV versus V or P for that matter, tell me how the graph will look. The y axis is PV and the x axis can be volume or pressure. I'm going to get the same graph. What kind of graph will I get?
Sir, a straight line like
Hmm.
parallel to the x-axis.
Absolutely right. So straight line parallel to x axis. I mean, that is not it. Right, you will get a straight line parallel to x axis. Why? Primarily because Boyle's law says this PV is constant, right? So different pressures, different volumes. When you're going to multiply, you're going to get the same constant, whatever it is. So that's how the graph looks, right? So fine, that's about Boyle's law. Second one is my Charles law. Okay, so Charles law is going to be at constant pressure, right? The volume of the gas, obviously pressure and the number of moles here also, and its constant temperature as well as the same amount of gas, right? Is there any doubt? Okay, fine, cool. So at constant pressure and number of moles, the volume of a gas is directly proportional to the temperature of the gas. Again, absolutely, it's gonna be in Kelvin. Please be very careful, right? Okay, so now I can say that V by T is constant, or I can say V1 by T1 equal to V2 by T2 is equal to V3 by T3, so on and so forth, is some constant K, right? Fine. So now if I plot a graph between temperature here and volume here, right? Now we are going to get a graph, right? Now tell me where the graph will start from. Will it start from origin? Okay, given that the temperature is in Kelvin scale. Oops, sorry. right? Given that the temperature is given in Kelvin scale, tell me whether the graph will start from origin or not. Hello? Yes, I think you're saying something. I'm not able to hear it.
It
Sir,
won't
no.
start from origin, sir.
Okay, correct. Can you tell me why?
Because the Kelvin scale is different.
Sir,
Oh,
volume doesn't exist at absolute zero. Sir.
Okay. So that's the way of looking at it. Or say, if I remember second law of thermodynamics, right? It says that 0 Kelvin cannot be reached, right? So either way, you are not going to start the graph from this thing. What is that? 0. That is here. You're not going to start because this tells me 0 Kelvin. So basically, the graph is going to start somewhere here. Okay. Oh, I'm sorry. Not like this. Again, it's starting at 0 Kelvin. Something like this. This is where it's going to start. All right. Why are you not joining? Come on. Oh God. Okay, better. That's how the graph is going to look. Okay. Now, if the same thing was plotted, when the same thing was plotted at 0, I mean, in Celsius degrees, right? At that time, definitely it can start with 0. That means it can start from here. Okay, right? Because I can have 0 degrees Celsius. That means it is just going to be 273 Kelvin. That is okay for me. Right. So please, when the choices are given, please look for what scale they have given, right? And accordingly, you choose the graph, right? So again, I can have different pressures, right? So isobars, I can draw. Isobars are basically going to be the graphs at constant pressures, right? So say if I take a graph here, here, right? Say this is P1, this is P2, this is P3. Again, can you just do it? Whatever we did exactly last time, can you do it and tell me what is the order of pressures? Make any one thing constant and just see how the other thing is varying and you will get the answer. Yes, any answers? Okay, you're going to do the same thing. Say I'll make volume constant, like something like this. Say this is P1, P2, and P3. Correct? Sorry, T1, T2, and T3, right? So I see that T3 is the greatest, okay, obviously because that's how the scale goes, right? So I know temperature and pressure are directly related. So P3 is greater than P1, sorry, P3 is greater than P2, it is greater than P1. Very simple. Or again, you can make temperature constant and you can see how the volume is varying, but at that time, please remember that pressure and volume are inversely related. So whatever you get is the order for volume, the opposite will be the order for the pressure. Okay, right? So hope you understand what I'm trying to say. Right, okay, that's about Charles' law. Next, third one is what is called as Gay-Lussac's law. Guys, Gay means happiness. Okay, fine. So here at constant volume, constant volume and number of moles, pressure is directly proportional to temperature. This is what is Gay-Lussac's law, right? So again, same thing, P by T is a constant, or I can say P1 by T1 equal to P2 by T2, so on and so forth, is a constant K, some constant, right? So you're going to get the exact same graph for pressure versus temperature as you got in the volume versus temperature. Again, you have to depend on what kind of scale you're using, whether you're using temperature in Kelvin scale or you're using it in Celsius scale, right? So same kind of graph. And lastly, the fourth law for gases. is what is Avogadro law. Right. So Avogadro law at constant pressure and temperature, the volume is going to be directly proportional to the number of moles. Right. Obviously, it's pretty straightforward, isn't it? More and more is the amount of the gas, more and more will be the volume, given that the pressure and temperature are constant. Right. So again, same thing, V by N or N by V is constant, or I can say V1 by N1 equal to V2 by N2 is some constant K. Right. Okay, fine. So now all these laws can be put together, right? All these laws can be put together, and what will you be getting? See, remember, these are not, I would say, mathematically proven things. Okay, right? Obviously, you can understand. I can give you real life examples for you to visualize all these four laws, right? But if you want to prove it mathematically, it is a little difficult. Okay, we don't have like any particular theory or any mathematical formulation which is going to help us. All these things, and even the ideal gas equation, all these things are just observations, and they are not, I would say, mathematically correct. And not mathematically, I cannot say mathematically incorrect, but it's just that you'll not be able to realize it mathematically. That's what I'm telling. Okay, so it's all going to be purely observational. I mean, experimentally, you do something and you observe, and based on that, you propose a law. It's like that, right? Okay, so now combining all this, I will be getting the famous ideal gas equation, which is nothing but dV is equal to nRT, right? And you have to be very careful with the R value, right? So R value, majority will be using 0.80821, or you will be using 8.314. 8.314 if you're going to use pressure and volume in SI units, right? Pressure and volume if you're going to use in SI units, that is, for pressure if you use bar or Newton per meter squared, and for volume if you use meter cube, right? At that time you have to go for 8.314. Right now, this when you have to use is pretty simple. If you use pressure in terms of ATM, right, and if you use volume in terms of ml or liters, right, at that time you'll go for 0.0821. Okay, right? Other than that, you will not be using any values, and 99%, I would say 90% of times you will be using 0.0821. Right. So 8.314 I'll be using for energy calculations. Hope you remember. In thermodynamics, most of the times you would have used only 8.314. Okay, right? So that is about your ideal gas equation. Now moving on.
Sir, volume in meter cube will give 8.314, sir.
Yeah, SI units. I've obviously this thing for a volume SI unit is meter cube. Pressure SI unit is bar. If you're
Sir,
gonna
1
use
meter
that,
cube is 1000 liters, sir.
yes, yes, yes. I can write that also. It will be very helpful actually. 1 meter cube is 1000 liters. 1 decimeter cube is 1 liter. 1 centimeter cube is 1 ml. So these three things you remember. It is really gonna be helpful when you do the problems. Okay, right? Fine. So moving on, now we have said something about the ideal gas, right? So all these things, all these laws, ideal gas equation, Boyle's law, that law, this law, all these things actually came into existence because of this. Kinetic theory of gases. Okay, now there are certain postulates, there are certain points given by kinetic theory, and based on that only all these scientists propose their laws, right? Okay, so we'll just look at the points, what it says, right? So first point is that or like say these gas molecules are point masses. That's what you need to understand. First postulate or first point told by kinetic theory of gases is says that the gaseous molecules are going to be point masses. Now you would have seen in so many these things, they will be representing gas molecules like this, just point, 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 point. Okay, now from this I will be able to get one say understanding. The thing is that if I compare the volume of one gas molecule, I just write GM. GM means one gas molecule, one GM. Okay, hope you understand. If I just take one gas molecule's volume, right now, that is very, 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 very less when compared to the volume of the vessel, right? Or this volume of the vessel is nothing but the volume of the whole gas. Now, so many gas molecules together will form the whole volume of the gas. So the other way of putting it is the volume of one gaseous molecule is negligible when compared to the whole volume of the gas. Okay, so that point you'll be able to infer from this, right? Okay, fine. That's the first point. Second point is that obviously we know that the gas molecules are going to undergo collisions. There are going to be two types of collisions. One, collision among the gas molecules. Second is the collision between the gas molecules and the walls of the container. And that is how the pressure is created. Hope you remember, right? So the thing is about the collisions, all these are perfectly elastic collisions. Right, all these collisions are going to be are considered to be perfectly elastic collisions. What do you mean by that? Physics, what do you mean by an elastic, perfectly elastic collision, people?
Once they collide, they travel back the same way. I don't know how to explain it.
Not can you speak in terms of velocity?
It's the same, sir. It doesn't change
Correct, right? So
after
for
the collision.
example, correct, right? So if I have two molecules coming like this, right, say this has v1, this has v2, or they can even have same velocity, v1 and v1, whatever it is. Now they will collide, and when they go back, right, when they go back after colliding, they are going to have the same velocity of what it had initially, v1, v2. Right, this is what is called as a perfectly elastic collision. So what do you mean by this is that because of collisions, the velocity of the gaseous molecules are not going to change. Okay, right, fine. That's the second point. Cool. Moving on. Third point is that there is literally no interactions between the gaseous molecules, right? So there's no interaction means there is no attractive force, there is no repulsive force, there's nothing between the gaseous molecules. Okay, so that's what it says, right? But again, it's pretty, we can easily understand it's not going to be true, right? Okay, that's how we'll disprove all this, and we'll take some other correction factors for all of these in some time. Okay, so but for now, these are the points given by kinetic theory. Okay? A lot of assumptions are there. Okay, fine. So that's about the third point. And fourth point is that the kinetic energy of the gas molecules is a function of temperature. It is directly proportional to temperature. Okay, it's not going to depend on anything else, right? It is just going to depend on the temperature of the gas, right? So you can easily ask me, sir, what about mv half mv squared? That is really not going to work because I'm going to consider these as point masses, right? So that way of looking at in the way of classical mechanics, Newtonian mechanics is really not going to helpful here, right? So we directly say that the kinetic energy is directly proportional to temperature. And I'll give you the direct equation. It's very, very important. Kinetic theory, oh God, kinetic energy is 3 by 2 kBT. There is a derivation for this, but we are not going for that. Okay, so the kinetic energy of any gas, this is for an individual one gas molecule. Okay, this is for one gas molecule. Say if I ask you, I have an oxygen molecule, O2 molecule, and say I give you the temperature, and you have to go to find this thing, right? You are going to find the kinetic energy easily. So this is for one gaseous molecule. Please remember that, right? Now this kb value, I know it's nothing but it's basically going to be 1 by r. Sorry, 1 by r will not work, right? It's going to be 1 point. Let me make some space. Right, so the value is 1.38 into 10 to the power 23. This is the value. Or 10 to the power minus 23. I'm sorry. 10 to the power minus 23. Okay, so this is the value for this Boltzmann constant. Hope you know what is kb. Kb is Boltzmann constant, right? So now the same kinetic energy can be expressed in terms of universal gas constant also. In that case, it would be 3 by 2 n okay, 3 by 2 RT. I'll just keep and I'll tell you how I can modify this, right? So this is 3 by 2 RT. Oh God, I just got a message from my college. Republic Day celebrations are going to be online. Wonderful. Pathetic. Okay, so anyways, let me come back here. So what I was telling, yeah, so kinetic theory, so kinetic energy can be represented in terms of R also, universal gas constant, right? Now in this case, the only difference between the last time and this time is here we talk about 1 mole of a gas. Okay, we're going to talk about 1 mole of the gas, but here we talk about 1 gas molecule. Okay, now this is for 1 gaseous molecule. Now if I ask you, if I have say some 200 gas molecules, it's pretty simple. You just have to multiply this value by the term, how many number of gas molecules you have, and that can be denoted by n. N talks about number of gas molecules. Okay, now here also, if this is for 1 mole of the gas, if I have say n moles of the gas, you just have to multiply this by n. Okay, right? So 3 by 2 n kBT, that is for n number of molecules of the gas. K is equal to 3 by 2 nRT, that is for n moles of a gas. And hope you remember how moles and molecules are connected. One mole of a gas contains how many gaseous molecules, people?
6.023 into 10 power.
Thank you so much. I do know it. Okay, so it's Avogadro number of gaseous molecules, 6.023 into 10 to the power 23. Right, so fine. So see, so this, from this, what you can understand from this statement, or from this statement, what you can understand is, irrespective of whatever the gas I have, as long as it is ideal, that means if it is going to, what do you mean by ideal gases? If it's going to follow all these points, right? If it's going to strictly obey all these points, right? As it doesn't matter what gas you have, either it's helium or hydrogen or nitrogen or oxygen, at a particular temperature, all of them will have same kinetic energy. Is it not? Because you see, do you have anything related to the gas molecule here? No property, nothing, right? It just is a function of temperature. Here also, it's just a function of temperature, right? So no matter what type of gas you have, as long as an ideal gas, all ideal gases at a particular temperature will have same kinetic energy. That's what your kinetic theory of gases says. Okay, did I miss out any other point? I think no, right? So these are all the points given by your kinetic theory of gases, and on all these points, if it's strictly obeyed by a gas, those are what are called as ideal gases. Okay, and obviously ideal gas equation, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, all these things all should be followed for a gas to be ideal. Cool, right? So moving on. Right, so we will talk something about the velocities. Okay, so we said that say if I have 1,000 gas molecules, right, in a particular vessel, say there might be 1,000 different velocities, or say 10, say 100 of them will have some velocity, 300 of them will have some other velocity, 500 of them will have some other velocity, right? So there can be so much distribution of gaseous the distribution of velocities among gaseous molecules. Okay, so if at all we try to interpret, if at all we try to understand how this dynamics works, right? So there was this guy, a famous guy, you must have known him, right? His name is Maxwell, right? So he tried to give us an understanding of how the velocities are distributed. Okay, velocity is distributed among the gaseous molecules. Okay, now obviously these velocities are going to be functions of temperatures. That's obvious, because you can see kinetic theory is half mv squared. So obviously the velocity is also going to be directly proportional to temperature, or even in physical sense. If you just look at it, thermodynamics, if you look at it, if I'm going to supply more amount of energy, right? So the gas molecules are going to absorb it and they're going to move faster, right? So anyways, all these things are given by Maxwell. So we are going to see it in the form of a graph, right? So it's called Maxwell's velocity distributions. Okay, it's called Maxwell's velocity distribution curve. Okay, right, fine. So we'll see how this looks. Okay, right. So here, I'm going to have the number of gaseous molecules. Actually, I don't want to confuse it. That's why I'm writing like this. It's actually going to be dn naught divided by n. So in the sense that if I have n number of gaseous molecules, how many of them are going to have a particular velocity? So that's what it means. Okay, that's hope you understand what I'm trying to say. So if I have 1,000 molecules, okay, say 100 of them is going to have velocity of say 300 meter per second, right? Say another 100 of them are going to have some other value, right? So what I'm trying to say is, am I doing it correctly? Yeah, I'm doing it correctly. Okay, so with the velocity is going to be in the y-axis. Okay, right. So we'll see how the graph looks, right? So this is how the graph is going to look. Okay, this is how, actually it should be a little more pointed.
Sir, what is there on the y-axis?
I'll tell you again. Wait. I'll tell you. If I explain the graph, then it will make a lot of sense. Okay, fine. So this is how the graph looks. Okay, so again, I'll explain you what is this term, right? Say this talks about a group of number of particles. Okay, say like, let me put it this way. Okay, say this number, what you have is a very small number, right? Say, I don't know, let me assume the total number of gas molecules I have is 1,000. Okay, so this value is pretty small. Say the value is say some 50. This value is here is 50, right? So what do I mean by this is that 50 molecules have velocity of say this v1. Okay, say now if I go a little higher, if I take this particular value, say this is some 100, right? Say these 100 molecules are going to have a velocity of say v2. Okay, hope you understand do you understand, Varun, what I'm trying to say?
Yes, sir.
Okay, so this basically talks about the number of particles out of the given out of the total particles, some particles we are taking. That's what it means. Okay, fine. So that's how the graph looks. So what you see here is that this is the smallest velocity I can get in this graph, and this is the highest velocity I can get in this graph, right? Okay, now let me give you an analogy. Right, say you are in a very crowded bus. Okay, you are in a crowded bus, right? Say now the bus is going to stop. The bus is moving, then the bus is going to stop now, right? So you will see there will be some say some number of people who will just rush to get out, right? That'll be some small number, right? Now the other extreme case is that if the people are so lazy, some like very small number of them are gonna be wait for everybody to go and then they will come out, right? But majority of people, what will they do is that they will just try to go along with whomever is going. Intermediate velocities. Okay, so what I'm trying to say is that you have the smallest velocity here. This is the highest velocity here. For both these, the number of particles are going to be little less, right? That means molecules having very small velocity and molecules have the number of molecules having very high velocities are pretty less, right? Most of these gaseous molecules are going to have some intermediate volume, right? Say among the 1,000, say 500 of them or 700 of them are going to have these intermediate velocities. Intermediate in the sense is starting from here till here, right? These are the intermediate velocities. Among this, I'm going to have say maximum number of particles, right? Now I'm going to have one particular velocity, right, where the number of molecules are very high, is it not? So I would say this particular velocity is possessed by maximum number of molecules, right? This velocity is possessed by maximum number of molecules, right? So so that I'm going to give a special name. Okay, the velocity which is possessed by maximum number of molecules in a given number of gaseous molecules, that velocity is what is called as VMP, most probable velocity. Okay, I think the name explains everything. Okay, most probable velocity is the velocity which is possessed by maximum number of gaseous molecules in a vessel. I say how many ever gaseous molecules you have, majority of them are going to have this particular velocity. That's why it's called most probable velocity. Okay, right. So now I told you that you will be able to visualize what happens if I increase the temperature, right? So that if I do,
Sir, which point on the graph shows the most probable velocity?
I'll show you. Right, that's a very clumsy graph. Let me draw it here again, then I'll show you. Okay, so this is the number of particles. Okay, this is velocity. Okay, so if the graph something like this one, this velocity is what is VMP. Okay, you can see that's the maximum number of gaseous molecules I have, and the velocity possessed by them is the maximum, I mean, the most probable velocity. Yes, understood? Okay, fine. So now if I increase the temperature, if I increase or decrease the temperature, we'll see what happens. Right. So assume that this is a temperature T1. This graph is a temperature T1. Right. So now if I assume that I'm going to increase the temperature to T2, right, I'm going to increase the temperature to T2. So you will see that this is what is happening. This is a temperature T2. Okay, now if you just analyze this graph, if you just look into it very carefully, right? So what had happened is the most probable velocity has increased. This is mu mp2 and this is mu mp1. Obviously, this is greater. Correct, right? And I can say almost all molecules have actually increased their velocities. Is it not, right? Say that still there are three categories. One, most probable, the maximum velocity, and the minimum velocity, right? So compared to the last case, all these three velocities has increased. Is it not? Now you can see actually the graph is not that correct. It has to start somewhere here. It's, oh my god, where is the undo button? Okay, thank you. Okay, right. So the graph should have actually started from somewhere here, right? That would have been a better this thing. But what you have to understand is if I increase the temperature, the minimum velocity, maximum velocity, as well as your most probable velocities, all those things would have gotten increased. Okay, so anyways, this is just a physical picture, right? So this is like, even though you don't have to worry much about the temperature changes, but you have to understand what is most probable velocity. That's what is most important from here. Okay, right, fine. So there are other two more types of velocities. One is this, right? And also I have something called as V RMS. Okay, I think you must have done this so many times in physics, right? Root mean squared, right? So it's pretty simple, right? So root mean squared means what? I will take, say, if I have 1,000 molecules having 1,000 different velocities, say I'll take the individual velocities v1 squared, v2 squared plus v3 squared, so on so forth, right? Divided by the total number of gaseous molecules, and I take a square root of this, only the numerator. Okay, that is what is called as VRMS, root mean square. Right. Same way, I have something called as U or V average, and I think that is straightforward, pretty simple. V1 plus V2 plus V3, so on so forth, plus Vn divided by, again, plus Vn should be there. Okay, so Vn squared here also, right? So divided by n, this is what is called as your V average or U average, right? But obviously, it is impossible for us to determine all these individual velocities, right? It is really impossible for us to do it. I would say it's not nearly impossible. It's not possible at all. Okay, but again, I have some derivations, right? There are mathematically I'll be able to visualize it, but I am not going to go through all that. I am directly going to give you the formulas. Okay, so you're going to have three formulas: one for most probable velocity, RMS velocity, and average velocity. Okay, fine. So first, oh, I should be, hopefully I should be correct with this. See guys, actually I don't prepare anything, right? When what is there? And I don't carry any notes. Maybe if at all I take you an offline class, maybe you'll understand. When I come into the class, I just carry the marker, right? So the only thing which I use to teach is my mind. Whatever I remember, that's what I teach. And obviously I have become so used to it, and I am in constant touch with chemistry because I'm studying also, right? And that's why I don't carry anything. And actually it's a very proud thing for me, right? Because I've seen so many faculties, like not like my colleagues who are so-called so amazing teachers having so great feedbacks. Everybody carries at least a piece of paper, right? So that's why I am generally, if I feel that I am not confident, I'll not tell you. I rather not tell you. I don't want to tell you something which is wrong. Okay, so please bear with it. Okay, so MP, that is your most probable velocity, is root of, and hopefully I'm correct, I should be correct. Okay, it's root of 2 RT by M, right? So root of 2 RT, R again should be in terms of 8.314, because I'm using velocity in SI units. I want the velocity in meter per second, right? So that's why I use SI unit. And if that's the case, I have to go for 8.314. Okay, 8.314, and T should be in Kelvin. Okay, right? And this M is the molar mass of the gas. Obviously, it's going to depend on the gas. Okay, molar mass of the gas. Okay, fine. So if it's oxygen, you have to put 32. Remember, it's O2, not oxygen molecule, not oxygen atom, right? Okay, so that's the formula for mu MP, that most probable velocity. Okay, fine. Then your RMS is root of 3 RT by M. Okay, so you can just remember 2 RT for most probable velocity, 3 RT, root of 3 RT by M for RMS velocity, right? Average alone is going to be little different, right? It's going to be root of HRT by pi M. Okay, root of 8 RT by pi M. Pi again is 3.14. Rest all the things are same.
Under the root?
Sorry.
Is M also under the root?
I don't get your question.
Is M also under the root?
Yeah, M is under the root. Yes, everything is under the root.
Okay.
Actually, yeah, correct. I should have done it. That's my handwriting. Please bear with it. Okay, M is also under the root. Yeah. Okay. So yeah, these three are the formulas, and definitely questions will come from this, right? And a very famous question is, they will ask you the ratios of this versus this versus this. Okay, so you, like, I forgot the number. It is like 1 is to 1.18 is to something, but I'm not sure. See, please check your books if you follow any reference books, right? So definitely those values are given, right? The ratios of most probable velocity versus RMS velocity versus average velocity, they might ask. Okay, right? Fine. So please be careful with that. Okay, so that's about the velocities. Okay, fine. The next thing is, since we're talking about velocity, since we're talking about movements, right, we will spend some time on this particular phenomena. Okay, diffusion or effusion. Okay, fine. We know what is diffusion. Diffusion is basically going to be the movement of gas, or say in general, diffusion is movement of anything when I have concentration gradient, right? So obviously, if I have an area which is okay, if I have say there is this thing like this. Okay, say now at this side, the concentration Okay, the concentration increases this side, right? So obviously, if I have a solute particle, it is obviously going to move from the lower concentration side to the higher concentration side. Pretty simple, right? So as if at all you want to see in the form of a gas, it's pretty simple, right? Say if I have a vessel, right, and say there's a partition here. Excuse me. Sorry. Right. Okay. So if I have a plate which is covering, which is dividing these two parts, and say there are gaseous molecules only this side, right? So obviously, as soon as I remove this, right, you will see that the gas molecules are going to go from this side to this side. So obviously, here I had higher concentration. Oh God, sorry guys, this is absolutely wrong what I wrote here, right? Say if this side the concentration is increasing, you will see that the gas molecules are going to move from the higher concentration side to the lower concentration side. I mean, not the gaseous molecules, solid particles. Okay, anyways, right? So you know already what diffusion is, right? So yeah, if I remove that plate, right, you will see that the gas molecules are going to go from the higher concentration side to the lower concentration side. This is what is called as diffusion, right? Now, what do you mean by effusion? Can anyone tell me what is effusion, or any practical example of effusion? Any guesses? Okay, nobody knows. The perfect example is your deodorants, like the sprays which you use, right? So I would say effusion is diffusion, but if it happens through a very small hole, that is what is called as effusion. Say if at all I want to give you a physical picture, this is how it is. Say I have a vessel which is closed, right? Inside that I have gaseous molecules, right? Now, if I put a small hole here, obviously you see that the gas molecules are going to come out, right? So this phenomena is what is called as effusion. Okay, hope you understand the difference between effusion and diffusion, right? Diffusion is because of concentration gradient. Here also it's because of concentration gradient, but you are actually making a hole so that this happens. This is not going to happen on its own, right? But this happens on its own. That's how you see it, right? Any questions? Okay, fine. So hope you understood the difference between effusion and diffusion, right? Now we will see what are all the factors which will affect the rate of diffusion or effusion, how fast a gas diffuses, how fast a gas effuses, right? Now all these things we'll see, and we'll try to give a mathematical picture to that. Okay, right. So the first factor which is going to affect my rate of diffusion, or actually we are seeing what are the factors which is going to affect the rate of right? We are going to see what are the factors which are going to affect the rate of diffusion. So the first one among them is definitely the mass of the gas. Is it not, right? Obviously, the thing which a higher mass will move slower, right? The one which is lightweight will move faster, right? So this I can definitely say for sure is gonna be inversely related to the this mass I'm talking about is the molar mass of the gas. Okay, say if I ask you, say if I have hydrogen gas and oxygen gas, which is gonna move faster?
Hydrogen.
Hydrogen. It's simple, right? Hydrogen has a molecular mass of 2, oxygen has a molecular mass of 32. So definitely the one with lower mass moves faster. Okay, right? Fine. So that's about the first point. Second point. This is definitely the temperature, right? So now assume that say a fusion process I take. Okay, now normally you do this, I will have say some rate R1. Now if I heat this gas and I make a hole, obviously what do you think? The gas molecules are going to come out really more faster, isn't it? So I will say have R2, which will definitely be greater than R1 because I have supplied more energy and the gas molecules will have higher velocity and they will come out faster. right? So the second one is definitely going to be temperature. So temperature is going to be directly proportional to the rate of diffusion or effusion for that matter. Okay, third one, right? Third one is about the pressure of the gas inside, right? Now, if I have very low pressure, obviously you see that the gas molecules are going to come out little slower. But if I have jam packed, they have just what to say, pushed so many molecules inside. So that means I have so much pressure inside. Obviously, as soon as you make the hole, the gas molecules are going to come out faster, isn't it? So pressure also is going to be directly proportional to see, I don't have to explain all this. If you just visualize it physically, right? Like the real life in the scenarios, if you just visualize it, I don't even have to explain all this. It's self-explanatory, correct? Right? Pressure is the one which is going to be directly related to the rate of diffusion or effusion. Right? Anything else? Obviously the number of molecules, right? The number of moles is a better way of looking at it, right? Because I know number of moles and number of molecules are related, right? So obviously more and more is the number of molecules, more and more will be the number of molecules coming out also, correct? So in this case also, you will be getting, it's going to be directly related to the rate of diffusion. Okay, so these four are the factors, right? Okay, now the next thing is, how do you calculate the rate of diffusion? Right? Not depending on all these factors, but individually, right? How will you calculate the rate of diffusion? Okay, now it's pretty simple, guys. The rate of diffusion or effusion for that matter, right, is equal to del P by time, or say del P by del T. In this T is not temperature, this is time, or you can even write in terms of volume, del V divided by del T. Say assume that initially I had a pressure of, I had an helium gas I had an helium gas in a vessel, closed vessel, right? Say initially the pressure was 1 atm, right? Now I made a hole, the pressure became 0.5 atm in 5 minutes, right? Initially, T initial was 1 atm, right? Now, after some 5 minutes, right, the pressure became 0.5 atm inside the gas. Obviously, pressure will decrease, isn't it? Because the gas molecules are coming out. Now, you can easily use this formula and find out what is the rate of diffusion. Same goes with volume. I had some, say, 1 liter of gas, right? Now it became 0.5 liters at 5 minutes. You can again calculate what will be the rate of diffusion using the formula del V divided by del T. Correct? Okay. So now, yes, now you know how to calculate the rate of diffusion. Now we'll just connect the rate of diffusion with all the factors which we saw. Okay, and the most important factor of them all is this mass. Okay, and you are not going to get questions from these. I mean, that's what I predict, right? Because I've never seen questions coming from any of these, right? But again, it's pretty easy. You will be able to correlate even if it is going to come. Not a big deal at all, right? So we will just see first Graham's law. Okay, Graham's law of diffusion. It's pretty simple. What does Graham's law say is that the rate of diffusion, right, is inversely proportional to the root of molecular mass of a gas. That's what it says, right? We just said that it is direct, it is inversely related, but it just gives more insight. How much is it inversely related? That's what this Graham's law says. Okay, so our rate of diffusion is inversely related to the root of the molecular mass of the particular gas, right? So now if I want to compare two gases, R1 by R2, right? For one is another gas, two is another gas, that would be equal to root of M2 by M1. This formula is the most important one. I mean, among diffusion, R1 by R2 is equal to whole root of M2 by M1. Okay. Now, if at all you want to correlate all these things with the same with pressure, temperature, and number of moles, I can do that. But that is not Graham's law. That is just what you are doing. So R can be, I can say it's directly proportional to the pressure, temperature, and the number of moles divided by the root of molecular mass. You can see because pressure is directly related, temperature is directly related, what is that, your number of moles is also directly related. Okay, so if they give you two gases, you just have to divide the terms and see what you're going to get. Pretty simple. But they're not going to ask you that. They will just ask you this, Graham's law. R1 by R2 is equal to root of M2 by M1. Right? Okay, so all these things are going to be related to ideal gases. Okay, till now whatever we have seen is all related to ideal gases. Right? Now obviously we know, if you look at the kinetic theory of gases points, you obviously see that there are certain points which we cannot accept, and that is the reason why no gas can behave ideally at all temperatures and pressures. Right? Now I will be able to make, oh god, wait, the charge is less, guys. I'll just put my laptop in charge. Just give me a moment. Okay, fine. So what I was telling you is something in the chat. Right? So we have seen all the things about ideal gases, right? So obviously, as I told you, there are going to be certain problems with respect to a kinetic theory of gases, right? So we have to do something about it, right? Now, first we'll see how is it that the real gases are not behaving ideally, right? How is it different? Okay, fine. So first plot is when I go for P versus V. Oh, no, wait. It's PV versus V. Okay, right. So when I go for a graph which is PV versus V, right? So what I expect for an ideal gas, I expect a straight line parallel to x-axis for an ideal gas because it follows Boyle's law, right? But you are not going to see this for real gases, right? Say sometimes you are going to see something like this, sometimes something like this, right? So it depends on what kind of gas you have, right? So I think this is going to be helium, and I think this is for nitrogen, if I'm not right, if I'm not correct, whatever it is, right? So the straight line just, you see there is a dip sometimes, and then the graph is going to increase, or straight away you can see that it is going to increase, right? Okay, so this is what happens when I have a real gas, right? But you do see that this graph coincides with the ideal gas graph at this particular point, right? This graph coincides with the ideal gas curve for a particular point. Correct, right? Now that particular point is, if you look at it, right? So I'm going to give a special temperature for that. Okay, so obviously this PV, right, is going to be a function of temperature. We know obviously PV is, if I even look at the ideal gas situation, it is going to be a function of temperature, nRT, right? So I'm going to give a temperature, right, where the ideal gas, when the real gas behaves ideally, right? So at the range of some temperature, at the range of some temperatures and pressures, right? So you will see that the gases will behave ideally, and that temperature is what is called as Boyle temperature, TB. And if at all you're going to consider the pressure there, it's going to be called as Boyle pressure, PB. Okay, right? So what if I ask you what is Boyle temperature, you're going to tell that it is the temperature at which a real gas can behave ideally. Okay, right? So this is one of the ways of looking at it, like say with the help of PV versus V or PV versus P graph, right? Now other way of looking at it is by using something called as compressibility factor. Okay, compressibility factor, which is denoted by the letter Z. Okay, right. Now, what is this? This is basically going to be, I would say, Z is defined as V real divided by V ideal. Okay, at a particular temperature and pressure, right? So the real gas will definitely have a different volume because it's not ideal gas, and obviously an ideal gas will have a different volume because it's not a real gas. I mean, it's complementary statements, right? Okay, so fine. Now, if it is an ideal gas, if I talk about an ideal gas, obviously these volumes are going to be same, right? So in that case, an ideal gas will have a compressibility factor of 1, right? Okay. Now, please understand, you can either speak in terms of volume, right, or you can even speak in terms of pressure, right? So if that's the case, I again write is going to be real pressure divided by the ideal pressure. Okay, real pressure divided by the ideal pressure is what is called as your compressibility factor. Again, Z value will be equal to 1 in terms of this if the gas is ideal, right? Okay. Fine. So we'll see how the this thing varies, right? How your what is that compressibility factor? If I put it in form of a graph, we'll see how real gases behave, right? So if you look into that, okay. So Z versus P or V doesn't matter. Say let me take P. Okay. Say now if it's an ideal gas, I know this value is 1. Right? It's going to be parallel to x-axis, right? And that value of compressibility factor for an ideal gas is 1, right? So again, you will see for real gas that sometimes it can be like this, it can be like this, it can be like this. Okay, fine. So that's what is going to happen, right? So one more thing I'll tell you, right?
Sir, I have a
Say
doubt.
these are isotherms. I'm doing all this at one constant temperature,
Sir,
right? Yeah.
sir, shouldn't it be P ideal by P real because volume and pressure are inversely related?
Correct. But if I tell you the another, there is another formula for Z, which is nothing but PV by nRT, right? So PV by nRT will be equal to 1 for an ideal gas. So you can
Yes,
see
sir.
both pressure and volume are in the numerator. That's why I take it like this,
Okay, sir.
right? Okay, good
Okay.
question. It's actually a good question. Nice. Okay, fine. So what I was telling is, yeah, so this is happening at a particular temperature. This is again, this is for different gases. Say this is for a gas X, this is for a gas Y. So gas X, gas Y, this is some gas Z, right? Fine. So if I take one particular gas, right? If I take one particular gas, and this is your ideal gas curve, this is Z, this is P or V, right? So if I take one particular gas and I just keep on increasing the temperature, right? If I take just say nitrogen, right? The gas actually here, this X is actually nitrogen. Okay. So say this is a temperature T1. Okay, right. So now what happens if I increase the temperature to T2, you will see that the dip is decreasing. This is T2, right? Again, you will see if I increase the temperature, the dip will still be decreasing. And at a point, you will see that this is gonna be exactly coinciding if I go for temperature T2. Again, obviously it's gonna increase after that. But you will see there is a range of pressure from here to here, right? At a particular temperature T4, the ideal gas equation and the real gas, ideal gas curve and the real gas curve are compensating. They're coinciding. Again, that is what is called as your boil temperature. So in this case, this T4 is what is called as your boil temperature. So what you have to understand is, if I take a particular gas and I plot the Z versus P for different temperatures, right? As I increase the temperature, the dip which you're seeing, the decrease and then the increase you're seeing, the amount of decrease is going to keep on decreasing. Hope you understand. Or in better words, in a better statement, if I say the dip, right, the dip is going to keep on decreasing if you're going to keep on increasing the temperature. And if you're going to increase the temperature after beyond T1, it's going to be a straight line. That's it. It is not even going to go down, right? Okay, now how do I get the physical sense of all this? Okay, right. Now, if I have to understand why the graphs are like this, right? Now, actually, I have to go for what are the wrong postulates, what are the wrong points told by your kinetic theory of gases. Okay, now I will just take one of the wrong points which are told, right? The point which I'm going to take is I'm going to take the no interaction point, right? One of the points said that there is no interaction, right? There will be no interaction between the gaseous molecules, and this is absolutely wrong. Right now, how will I prove it? Obviously, you know that the gas molecules can be liquefied, isn't it? So if at all the gas molecule can be liquefied, right? So I know the liquid molecules. I mean, among the liquid molecules, you are definitely going to have some amount of attractive forces existing more than the gaseous people, isn't it? So if that's the case, if I'm able to convert a thing where I have no interaction, where I'm going to have considerable interaction, that's actually not a case. That's actually a case which is really not possible. I should have had some amount of interaction before, and that interaction can be just increased or decreased. That can be done, right? But from zero interaction, getting an interaction, and from the same amount, that basically the same chemical compound only, H2O in vapor phase, H2O in liquid phase, the chemical composition is same, but you say that there are not going to be interaction, not believable, right? So that's the point which I'm going to take, right? And because of this interaction, again, obviously the interaction can be of two types, either attractive force or repulsive force. Okay, now we'll see what is the consequence of having this. Okay, now let me take my Z value. Right, now let me take a case where I have the Z value to be lesser than 1. Obviously, if it's equal to 1, ideal gas. Lesser than 1 or greater than 1, that's going to be a real gas. Right, so what happens here? I have this P real divided by P ideal. Right, so what do you mean by this is that the real, if I see that this value is lesser than 1, that means this value is less, this value is high. That means the P real is lesser than P ideal. That's what it means. Right, now let me try to explain this particular case with respect to the interactions. Right, okay, now say I have a vessel in which I have the gas molecules. Right, now assume that there between this particular gas molecule, come on, right, the mark one, obviously it is getting attracted by all the other gas molecules. Okay, it is getting attracted by all the other gas molecules. Right, now if this attraction was not there, okay, if this attraction was not there, can I say this is gonna move really freely and it is gonna hit the walls of the container with a greater force? Now let me give you a real life analogy. Right, say you are trying to move, you're going to go touch some wall and come back. You're trying to touch a wall, okay, and someone is pulling you from behind. Right, obviously if no one is pulling you from behind, you will be able to easily touch it with higher velocities. But say if someone is pulling you from behind, obviously the velocity at which you're going to hit the walls of, velocity at which you're going to touch the pole, right, is going to be less. Right, obviously if the force with which you're going to touch it is less, obviously the pressure is going to be less. So same analogy can be, you can bring it here. Right, if the gas molecule had no interaction, no attractive force, the pressure would have been higher, and that's what is my ideal gas. Right, but since you have some attractive force, right, since you have some attractive force, the gas molecule is not going to be that much free. Right, it is actually going to be restricted, so this pressure decreases, and this is exactly what is given here. P real is lesser than P ideal, and this will happen if I have attractive force. Right, and the part of the graph which tells me is the dip which you see here. Right, the dip which you see here, that's telling me at those pressures, right, at those ranges of pressures, I would say that the attractive force dominates. Right, okay, fine. Now I will take the other case when I have repulsive forces. Right, so there's a gas molecule, everybody is pushing it. Right, you are already trying to move and someone is giving you extra force of pushing you, obviously the pressure with which you will hit the walls of the container will be really high, right? And that's the case where I have Z greater than 1, or I can say that the real pressure is greater than the ideal pressure. Right? Okay. Right? Now, obviously, this will happen when I have repulsive forces happening. Right? Now, it's pretty easy to understand, guys, from the graph itself. Right? Now, you are increasing the pressure this side. Right? Now, when I have very small pressures, when I have very small pressures, that means what? The pressure is very less, means the gas molecules are a little far away from each other, isn't it? So whenever the gas molecules are far away from each other, I know it's just like a chemical bond. When they're very little far away from each other, the attractive forces dominates, right? Now, when I keep on increasing the pressure, when I keep on compressing the gas, right, the gas molecules will come closer, and I know if they're really close to each other, obviously their repulsive forces will dominate. Right? That's why you see after a particular point of time, the repulsive forces are dominating, and that's why you see that the Z value is greater than 1. Right? But at smaller pressures, since they're a little far away from each other, the Z value is lesser than 1. Okay, right? So I hope you understand how real gases are going to behave ideally. I mean, not ideally. Right? Okay, this is explained with respect to your attractive and repulsive forces. What is the time? Okay, right? So we are at the verge of completing the chapter, people. Right? So now obviously I have to correct all these things. Okay, the ideal gas equation is really not going to work for me. Right? So there was this guy. You want to name what is that guy who gave an equation for real gases? Who was a scientist? Hope you know what
Forgot,
equation
sir.
I'm doing. Sorry.
Sir, forgot the name, sir.
Okay. It's Van der Waals equation, right? The real gases equation. Basically, I'm going to see the real gas equation. Right. It is also called as Van der Waals equation. Right. It's also called as Van der Waals equation. Now, pretty simple. I mean, again, guys, there are a lot of inside stuff going on with this, right? But I'm going to directly give you the equation. Okay. Now, please understand, I am going to correct two things. Okay. What are the two things which I'm going to correct is about obviously the force, which we just saw now, right? The other thing which I'm going to correct is the volume. Right. Obviously, we said that the volume of the individual gas molecules are negligible when compared to the entire gas. Right. Okay. So obviously that is not going to be true, because you will be actually representing gas molecules like this. That would be better, because again, the gas molecules can be liquefied. Correct. Right. So for these two, I am just going to modify the ideal gas. I mean, not me. Van der Waals already did it. So Van der Waals actually modified the equations by just giving two correction factors, one for volume and one for pressure. I mean, sorry, one for force of attraction or repulsion. Right? Okay. So this is how the this thing looks. What is that? Your equation looks. P So P plus A n squared by V squared, V minus NB is equal to nRT. That's it, right? This is what is called as Van der Waals equation, right? So you see, this is what is your volume correction. This is your force correction. Okay, so you can see that there are constants A and B here. This A and B are what are called as Van der Waals constants. Okay, so A is the correction factor for force. You have to remember all this. At least you have to remember the equation. No problem is going to come from this. Do not worry. Nobody is going to give you A and B values and ask you to find some term. No, right? So you just have to remember the equation, and you have to understand what is A for and what is B for. A is the correction factor for F, that is force, and B is the correction factor for volume. Okay, and if you're really interested, you can actually look into why it's plus and why it's minus here. Maybe you can tell me next class tomorrow. You can tell me what exactly is this, right? Or I may tell you, but I think it will be better if you just search for it. Everything, if I tell you, then what's the point, right? Okay, so this is what is your van der Waals equation. Okay, now there is just one small topic which I have to complete, that is about the liquefaction of the gas, right? That will take some time, from 10 more minutes. Anyways, I'm not going to take your time. I'm just going to stop with this. Okay, I'll just take 10 more minutes next class and we'll go for problem solving. So please remember all the formulas we have seen and come to the class next, when you come to the next class. Okay, fine guys. If is there any question, I can address it now. Is there any question? Okay, fine. Thank you guys. We'll meet again tomorrow. I think tomorrow is Saturday. Yes, we have class. Okay, thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.